In this discussion, we're going to want to talk about ultra-short pulse MPEs. This is taken from the ANSI standard, the Z136.1. This is section 8.2.2. And what we want to do is in this discussion talk about this recommendation in the standard for when we want to determine an MPE for a pulse less than 100 femtoseconds. 100 femtoseconds is the shortest exposure duration in the tables, both ocular and skin. So what happens when we're dealing with a laser that has a pulse shorter than 100 femtoseconds? And boy, in these days, particularly with titanium sapphire lasers, we can run across lasers that have pulses less than 100 femtoseconds quite often in research labs and even in industrial where they're doing micro machining with ultra short pulses. But how do we determine the MPE? And the recommendation in the table is when we're dealing with the wavelengths between 180 nanometers to 1,000 microns, pulses less than 100 femtoseconds, we want to limit the MPE to the picoradians allowed for a 100 femtosecond pulse. And that's really what this discussion is about, because we get the question often from beginning students is what does it mean, the picoradians, limited to the picoradians, and how do you determine that in order to find the MPE for a pulse shorter than 100 femtoseconds, we take the MPE 400 femtoseconds and multiply it by the ratio of the real pulse duration divided by 100 femtoseconds. How do you equate this equation to this statement about limiting it to the picoradians? And we get that question because it may not be obvious how to move from radiant exposure, joules per square centimeter, because that's what the MPE will be offered in terms of what the MPE is for 100 femtoseconds. How do we move from radiant exposure to picoradians? And really, I think a more correct term for this is peak power irradiance. So let's start talking about this, because we do follow this recommendation because there's no other guidance. There's no other guidance offered here. And so in order to determine an MPE for an exposure duration or a time duration less than what the tables go to, we have to follow this recommendation. Otherwise, we've got nowhere to go. So let's pick a wavelength and take a look at the table, the ocular and skin tables. And I think what I want to do here is we'll pick 700 nanometers. We're going to be looking at this line right here that has 100 femtosecond time duration. That's our shortest exposure duration for our tables. And it tells us that the MPE is 1 times C sub E times 10 to the minus 7th joules per square centimeter. Now, we're going to be talking about a point source. C sub E is an extended source correction factor, and if we want this to be the point source MPE, C sub E is just set to 1. So our point source MPE for 100 femtosecond pulse at 700 nanometers is 1 times 10 to the minus 7th joules per square centimeter. Now let's take a look at the skin. Again, 700 nanometers, 100 femtoseconds. This is our MPE for 100 femtosecond skin exposure. It's 2 times C sub A times 10 to the minus 3 joules per square centimeter. It's radiant exposure. C sub A in this case for 700 nanometers is 1. So our MPE for 700 nanometer wavelength, 100 femtoseconds, is 2 times 10 to the minus 3 joules per square centimeter. Let's take a look at a little math. So you can see this is our MPE for 100 femtosecond pulse. And in order to get to peak power irradiance from radiant exposure, we just divide this MPE in radiant exposure by the time duration. Joules over seconds is power, which is watts. So what we're doing is we're converting the radiant exposure MPE limit to the peak power irradiance MPE limit. And that turns out to be 1 megawatt per square centimeter for an ocular exposure. And for the skin, it winds up being 2 times 10 to the 10th watts per square centimeter. Now remember, it said if you want to move to an MPE for a time duration shorter than 100 femtoseconds, we take the MPE for 100 femtoseconds and multiply it by the ratio of the real pulse duration divided by 100 femtoseconds. So we can see that all we've done here is, in order to hold this true for a 50 femtosecond pulse, we also, that's half of the 100 femtoseconds, we need to half the MPE. So 1 times 10 to the minus 7th multiplied by the ratio of 50 femtoseconds divided by 100 femtoseconds, that ratio, which is a half. Take this MPE, multiply it by half, that gives us 5 times 10 to the minus 8th joules per square centimeter. And of course, when we divide that by the exposure duration, we wind up with the same peak power irradiance as 400 femtoseconds, and that means by halving the MPE, we've limited the MPE to the MPE limit for 100 femtoseconds. And then we've just done the math, same math here for a quarter of a second, and you can kind of go through and see that it holds for the same for the skin. So that's all it really means, and you can see what how we've done the math in order to hold the peak irradiance to the 100 femtosecond MPEs. Okay, so what I'd like to do now is, let's just go to the software, and I've already loaded it up. 700 nanometers, we have 100 femtosecond pulse duration, and we can see that our MPEs are in fact, for the ocular, 1 times 10 to the minus 7th joules per square centimeter, and 2 times 10 to the minus 3 joules per square centimeter. If I half the exposure duration, so we'll go 50 femtoseconds, okay, you can see that yes, it does in fact half the MPE, and for both the ocular and the skin, and we've already seen through the math that by doing that, it limits it to the peak irradiance for 100 femtoseconds. And we'll just go ahead and put in the 25 femtoseconds, and we can see that, again, it's taken 25% of that MPE, and that holds then for both the ocular and the skin to the peak irradiance for 100 femtoseconds. So I hope that makes a little bit of sense and explains how we move from radiant exposure to peak power irradiance when we're talking about ultra short pulse MPEs. All right, that's it.